So in this video, I was planning on going over the problems that were posted for the review for exam number 3. And I'm going to go over the second set. And the reason why I'm not doing the first set is because I went over the first set in class. So this will just be the second set. So anyway, I'm just going to start with problem number 1. So for number 1, and I'll kind of read the problem and then go through the information. So, well, I'll write it down. So first of all, you have an elementary second order adiabatic reaction, and it's A plus B to C plus D. And it says you have a CSTR, and the feed is equimolar in A and B at concentrations of 2 moles per liter. So CA naught is equal to CB naught is equal to 2 moles per liter. The entering temperature is 310, so T naught is equal to 310 K. The volumetric flow rate is 20 liters per minute, so V naught is 20 liters per minute. And then it gives you some data for the reaction, and it says determine the temperature in the reactor and residence time for 80% conversion. So you're determining the temperature of the reactor, so T, and the residence time for 80%, so tau is equal to what when X is equal to 0.8. And then it gives you CPA is 25 BTU per pound mole Fahrenheit, CPB is 15, CPC is 15, CPD is 20, and these are all BTU per pound mole F. And then it gives you the heat of reaction at 300 K, and that's equal to minus 8,000 cal per mole of A. And then it gives you the rate constant at 300 K, and this is equal to 0.0005 mole per minute, and E is equal to 10,000 cal per mole. So we have all this information, and we want to determine the residence time tau, and we want to determine the temperature in the reactor at that time. So first thing we want to do is the mole balance. So mole balance, and this is CSTR, so that is V is equal to FA naught X over minus RA, and then we need the rate law. So it says it's second order elementary, so we know that the rate is K CA CB, and the stoichiometry, because now we need CA and CB, is CA, and I'm assuming this is liquid, so CA is equal to CA naught 1 minus X, and CB is CA naught, oh yeah, CA naught 1 minus X. So then you can combine these, and you get V is equal to FA naught X over K CA naught squared 1 minus X squared. And then let's see, I'm going to erase some stuff real quick and then continue with this. Okay, so then we can take this, and first of all we know that FA naught is equal to CA naught V naught, and so if we plug that in, so I'm going to put in CA naught V naught, and if I do that, this cancels. So then we have that V is equal to V naught X over K CA naught 1 minus X squared. And then we can divide over V naught, and I'm going to, yeah, so V over V naught, and that's equal to tau, which is what we're looking for, and that's equal to X over K CA naught 1 minus X squared. So now we get to the point of where it's kind of the new stuff. So by this point, you should be able to just go through this stuff and barely have to think about it. Like you should just be able to write it down. So anyway, now we need, first of all, we need K, because we know K at one temperature, but we don't know what it is in the reaction. And so we need, to calculate K, we need T, and so we need to do an energy balance to get T. So this said that it was adiabatic, but delta C sub P does not equal 0. So you would be in trouble if you just pulled the adiabatic equation off of table 8-1. So just make sure that you're using the right equation. So if delta C sub P isn't 0, then you need to use this equation. So T is equal to X multiplied by the heat of reaction at this reference temperature plus the sum of theta I CPI T naught plus X delta C sub P TR. And this is all over the sum of theta I CPI plus X delta C sub P. So then this right here, the sum of theta I CPI, in this case that's going to be theta A CPA plus theta B CPB. And the reason why you don't, I mean technically you also have plus theta C CPC plus theta D CPD, but theta C and theta D are 0, so theta A is 1, and theta B I believe is also 1 because you have, yeah, because they're equimolar, so theta B is also 1. And you know CPA and CPB because they were given. And so we need, and then this is the same as that. And then we need delta C sub P. So delta C sub P is equal to CPD plus CPC minus CPB minus CPA. And that was equal to minus 5. So then if we plug everything in, we know it gave us X. We know that X is 0.8. We know the heat of reaction at this reference temperature. We know CPA and CPB. We know T naught. We know delta C sub P because we just calculated it. We know the reference temperature. So anyway, if you plug all that in and calculate T, you get that T is equal to 489 K. So then what we can do with that temperature is plug it into our equation to calculate K at this temperature. And then we can go back to our mole balance and calculate tau. So I'm going to erase this stuff real quick. Okay, so for K, we have that K is equal to K that was given at 300 multiplied by the exponent of E over R 1 over T, I'm going to call it K1, T1 minus 1 over T. So then if we plug in our value for K1, so, well, I'll just write it down. So K is 0.0005 multiplied by the exponent of 10,000 over 1.987. And I didn't plug in units here, but just make sure that you're using the right gas constant when you use these equations, because it depends on what your units are in E and also in the heat of reaction if you're using that equation. So anyway, this is 1 over 300, because we know K at 300, minus 1 over 489, because that's what the temperature is in the reactor. And so this is equal to 0.326 liters per mole minute. And so then we know everything to calculate tau. So we know that tau is equal to x, which was 0.8, over, and we just calculated K, 0.326, multiplied by Ca naught, which was 2, multiplied by 1 minus 0.8 squared. So that was equal to 30.7 minutes. So when you're doing these problems, I highly recommend putting in the units just to make sure everything cancels out correctly and you're getting the units that you think you need to get, because for instance with this, if you put in all your units and then you didn't get some time here like minutes or seconds, then you know that something's wrong. And like with this, if you use the wrong gas constant, then you won't get the right K. So when I do these in my personal notes, I always write in the units. I don't always write them on the board because it takes a lot of time, but I just highly recommend doing that, because then you know that you're doing your problem right and you know if you need to do a conversion, and I feel like it just makes things easier. So that's the take from that. And as far as this problem, really the only new thing was calculating this energy balance, and everything else was pretty much the same. So you just did the mole balance, rate law, stoichiometry, combined everything, and you could solve this algebraically because you have a CSTR. And then in this case, you just added the energy balance because you had a non-isothermal reactions. So anyway, I'm going to erase this and do number 2. Actually, I just want to show you this real quick. So in the notes that you have for the exam, he said that he was going to give you a table with the gas constants, but I'm not sure if he's going to give you a table with the energy balances. So if I were you, I would probably put those in your notes. And just to kind of show you what I did, so depending on what, like in this case, you had an adiabatic CSTR, but delta C sub P wasn't 0. So you couldn't just use this equation on table 8-1, it's the first one, for an adiabatic reactor, because that equation assumes that C sub P is 0. So what I did was I physically wrote in my book, and I wrote, I don't know how well you can see that, but I wrote next to it the equation for the case of where it's not 0. So then it's just there with that one. So, and I did that with a bunch of these equations, like anywhere that there were some differences, like because you have the assumptions for the equations in the table, and then there might be cases where if you're making a different assumption or you didn't make that assumption, then the equation is slightly different. And so I just physically wrote the other equation in here too, just so that they're all in one place, and I felt like that was really helpful. And then I would also recommend putting the general energy balance in your notes. That's the one that you need if your work is not zero, because all of the equations in this table assume that the work is zero. So that's just something that might be helpful. Okay, so for number 2, it says you have a second order reversible liquid phase reaction that's in a CSTR at 350 K. The feed is equal molar in A and B of 1 mole per minute each. And then it gives you the reaction, which is A plus B to C plus D, and it's reversible. And the following parameters are given, and then it gives you some parameters. And then it says determine the reactor volume for 82% of the equilibrium conversion. So in this case, we're not calculating the reactor volume at 82% conversion, we're calculating it at 82% of the equilibrium conversion. So in order to figure out what the conversion is, you need to calculate the equilibrium conversion and then multiply that by 0.82. And then after you do that, you should be able to figure out the reactor volume from the mole balance. So this is 2. So it's second order reversible. So CSTR, T is equal to 350 K, FA naught is equal to FB naught is equal to 1 mole per minute. And the actual reaction is A plus B to C plus D. And then CPA is equal to CPB is equal to CPC is equal to CPD, and that's equal to 40 joules per mole K. Your heat of reaction at 300 K is equal to minus 10 kilojoules per mole. K at 330 Kelvin is equal to 3. This is actually capital K, so KE, I guess. K forward at 360 K is equal to 0.5 liters per mole per minute. And E is equal to 50,000 joules per mole. And this says determine V for X is equal to 0.82 of the equilibrium conversion. So I'm going to start this problem with a mole balance. You could do this a few different ways. You could calculate the equilibrium conversion first and then get X because you know you're going to need it. But I just like to approach all these problems the exact same way because then there's no room for confusion. And so if you go through it like say you were confused about this, then if you just write down the mole balance, then right away it's like, oh, I need X. I need the rate. So then you write that down. And then it's like, oh, from the rate, I need the concentrations. So then you write those down. And then you just combine everything. And then it's like, oh, I need K. So then you calculate those. And then you can easily calculate your equilibrium conversion because you've already written down the rate. So, I mean, you can do these problems however you want, but that's how I do them. And I feel like it's just a lot more straightforward than trying to go through in a way that's not very ordered and then you just get confused trying to figure out which equation you need. So, because these problems have a lot of equations, and so it's just better to keep them all organized. So anyway, for the mole balance, V, and it's a CSTR, so V is equal to FA naught X over minus RA. The rate law, we know that it's second order reversible, so minus RA is equal to K forward CA CB minus CC CD over KE. Stoichiometry, CA, and I don't remember if it said, but I'm assuming this is liquid, so this is CA naught 1 minus X. CB is equal to CA naught 1 minus X. CC is equal to CA naught X. And CD is equal to CA naught X. So I'm going to erase some stuff and then combine these. So then if I combine these, I have minus RA is equal to KF CA naught squared 1 minus X squared minus CA naught squared over X squared over KE. And then I want to pull out CA naught. So this is equal to KF CA naught squared 1 minus X squared minus X squared over KE. So I'm going to need KF and KE. They were given to us at some temperature other than what our reaction is. So for K, this is equal to KE, and I'm just going to say KE1. This is the one that was given at 330 K multiplied by the exponent of the heat of reaction over R, 1 over T1 minus 1 over T. So then if I plug everything in, we were pretty much given everything. We were given the heat of reaction. We can figure out what R we need by looking at the units on the heat of reaction. T1 was 330 K, because that's what this was given at. And this was 3. So anyway, if you plug everything in, you get that this is equal to 2.44. And then K forward is equal to, I'm just going to say KF1 multiplied by the exponent of minus E over R. Actually, this isn't minus. That's E over R, 1 over T1 minus 1 over T. And then if you plug everything in, you get that this is equal to 0.31. So E was 50,000 joules per mole, T1 was 360, and T was 350. So anyway, you get 0.31. So now we can take these and we want to calculate the volume. So we need to calculate the rate, and so we need to know what X is. So now we need to calculate this X, well, this equilibrium conversion, so then we can calculate X. So I'm going to erase some stuff real quick. So for equilibrium, we know that the rate is equal to 0. And so if we go back to the equation I had for the rate, that was minus RA is equal to KF CA naught squared 1 minus X squared minus X squared over KE. So if we set this to 0, we get that 1 minus X squared is equal to X squared over KE. And I'm going to write xe on these so that we know that this x is referring to the equilibrium conversion. So then we can solve this. We know what ke is because we just calculated it. So we get that xe is equal to 0.6094. And so then x is equal to 0.6094 multiplied by 0.82, and that's equal to 0.5. So then we can calculate the rate by plugging this into here and here. We know kf, we know ke, we know ca naught. So if we do all that, we get that the rate is equal to 0.1828. And then we should know everything for this. We know fa naught, we know x, and we know the rate. So if we plug all of that in, well, I'll just write it down. So v is equal to fa naught x over minus ra, and this is equal to fa naught, which was 1 multiplied by 0.5 over 0.1828, and this is equal to 2.74 liter. Okay, so for number 3, it says you have an endothermic reaction in a CSTR. The steady state temperature in the reactor is 27 degrees C. It's surrounded by a steam jacket where the saturation pressure of the steam is 11.5 psia. The heat transfer coefficient between the jacket and the reactor is 225 with a heat transfer area of 15 feet cubed. At steady state, or 15 feet squared. At steady state, what is the rate of heat transfer from the jacket to the jacket or from the reactor in kilojoules per hour? And then it gives you some additional information. So first of all, we know that this is a CSTR. It's endothermic. The steady state temperature is 27 degrees C, which is 80.6 degrees Fahrenheit. It's surrounded by a steam jacket, so steam jacket with the saturation pressure of 11.5 psia at 200 degrees F. U is equal to 225 BTU per hour foot squared F. A is equal to 15 feet squared. And so then at steady state, it's asking for Q. So this is really simple. If we make an assumption and we say that the temperature of the steam, or the temperature of the whatever's in the jacket is the same through the entire thing, so basically TA1 is approximately equal to TA2. So this is the entering temperature in the jacket and the exiting temperature in the jacket. Then Q is equal to UA TA minus T. And so then this is equal to 225 multiplied by 15 multiplied by 200 minus 80.6. And so this is equal to 402,975 BTU per hour. But I think it asked for kilojoules per hour, so then you just need to convert the BTU to kilojoules. And so that would be 425,161 kilojoules per hour. So for number 4, and he has specifically said that there won't be a multiple choice problem on the exam, but you could still end up with a problem like these multiple choice problems, and instead of having a list of possible answers, you'll just have to write down what the answer is. So for instance, number 4, it says for the reaction conditions shown below, if the heat of reaction increases from minus 50 kilojoules per mole to minus 80 kilojoules per mole, then A, does the slope of XEB versus T-line increase, the slope of XEB versus T-line decrease, or the slope, or it remains the same. So instead of having these options, you would just write down whatever the answer is. So just, even though he said there might not be a multiple choice, definitely still study these. So anyway, for number 4, you have, so first of all, this is irreversible. It's exothermic. The heat of reaction is minus 50 kilojoules per mole, and it's increased to minus 80, or actually it's changed to minus 80 kilojoules per mole. UA is 0, and T naught is 300 K. So basically it's asking what will happen if XEB, if you plot XEB versus T, so let's just say this is your plot, so X, EB, T, and let's just say that this is the original, so let's just say that this one is when the heat of reaction is minus 50 kilojoules per mole. So then if you plot, so first of all, I'll write down the equation I'm looking at. So X EB is equal to sum of theta I CPI T minus T naught over the heat of reaction. And the reason why I'm using this equation is not necessarily because it's adiabatic. I don't know if it is or not. The reason why I'm using that equation is because it specifies that UA is 0. So maybe that means that it's adiabatic. So anyway, if we just look at this, we can already see that if we increase this, this has to go down. So this will end up looking something like this for the case of the heat of reaction being minus 80 kilojoules per mole. So then we can say that as the heat of reaction increases, you'll have a higher temperature for each conversion. So the slope of this line decreases. So then the answer for this is B. And one thing about these problems is you might end up with a problem like this where it says, okay, UA changes, or the heat of reaction changes, or T naught changes, and you should have a general idea of what happens with your plots when you change certain parameters, and you can kind of get a feel for that by either just writing a quick MATLAB program and playing around with variables to see what happens, or I was told that there's a module that you can download from the book author's webpage, so that would be the Elements of Chemical Reaction Engineering by Fogler. So if you go to his webpage, there's apparently a module that you can download that you can go through and change parameters and see what happens. So I highly recommend doing that because it's going to be a lot easier to figure this out on the exam if you already have a general idea of what happens versus having to like physically plot something. Alright, so for number 5 it says the following reaction is taking place in a PFR. And then it gives you some information. It's elementary, reversible, endothermic. And it says an engineer, Mr. Rickless, contends that the reactor must run at as high a temperature as possible to obtain the highest possible conversion. His colleague, Mr. Lim, says that a conversion limit will be reached and multiple reactors with interstage cooling will be required to achieve high conversion. Who is right and why? So I'm just going to write down some information real quick. This is number 5. So first of all, we know it's a PFR. It's elementary. It's reversible. It's endothermic. The heat of reaction is equal to 100 kilojoules per mole. UA is equal to 100. TA is equal to 400 K. Actually, this is T naught. And TA is equal to 450 K. So, in order to figure this out, I think the main thing that will help is knowing that it's endothermic. So, what we can do is look at what XE will look like for, because we also know that it's reversible. So, this is, whoops, XE versus T. And so just a generic plot for an endothermic reaction, XE looks something like this. So basically there's no limit on conversion as you increase the temperature. So the answer for this is going to be that increasing the temperature to the highest temp possible will get the highest conversion. And just to compare this real quick, so this is endothermic. So just to compare this real quick, if this were exothermic, then your curve XE would look something like this. So, and so then in this case, increasing the temperature would actually decrease your conversion. So the reason why it's the case with this one is because your reaction is endothermic. So for number 6, it says for the given reaction conditions, as UA increases, the XEB versus T line does not change, increases in slope and shifts to the right, shifts to the left, or decreases in slope. And then it gives you some information. So this is 6. As UA increases, X, EB versus T does what? So first of all, we know that this is irreversible. It's endothermic. The heat of reaction is equal to 100 kilojoules per mole. UA is 0 initially until it's increased. T naught is equal to 300 K, and TA is equal to 330 K. So if we look at the energy balance equation, it is energy balance is equal to UA over FA naught T minus TA plus the sum of theta I CPI T minus T naught, and that's all over the heat of reaction. So then if we plot this, and I actually physically plotted this in MATLAB just to see what it looks like, so you might want to do that. But just the generic plot, when UA is equal to 0, you get a line that looks something like this. And the reason why it looks like this is because it's endothermic. So if it was exothermic, it would go this direction. So this is the case of UA equals 0, and this is T and X energy balance. So then if I, and then I put in the UA, because it says UA increases, so I just said UA was equal to 100. So then if you do that, or so when I did that, I got something that looked kind of like this. So UA equals 100. So the correct answer for this is that, first of all, you have an increase in the slope. So increase in slope, and a slight shift to the right. So shift to right. So then the answer for this is B. All right, so for number 7, it says, the following reaction is taking place in a CSTR. In order to ensure a high conversion steady state, the engineer should A, increase the feed temperature, B, increase UA, C, decrease the feed temperature, and then it says justify your answer with a qualitative plot, and then it gives you some information. So this is number 7. So it's a CSTR, it's irreversible, it's exothermic. The heat of reaction is equal to minus 75 kilojoules per mole. UA is equal to 0. T naught is equal to 300 K. TA is equal to 320 K. And so what we can do is look at just kind of look at a generic plot to see what's happening. So if we plot G of T, it should end up looking something like this. And then we can look at R of T. So R of T will look something like this. So this is G of T. That's R of T. So then just eyeballing this plot, so this is T naught right here. Just eyeballing this plot, if we can move this, if we can shift R of T over, it should hit this G of T curve at a higher point. So let's just say that we shift this to like right here. So then that will end up hitting it up here somewhere. So then that should be a higher conversion. So the right answer is that you would increase the feed temperature. And you can kind of play around with these G of T and R of T equations to kind of get a better idea of what happens with them. So G of T is equal to the negative heat of reaction multiplied by minus RAV over FA naught, and that's equal to the negative heat of reaction multiplied by X. And R of T is equal to CP naught 1 plus kappa T minus TC, where kappa is equal to UA Cp naught, Fa naught, and Tc is equal to kappa Ta plus T naught over 1 plus kappa. And I don't want to go into a lot of detail about these here because I just want to get through the problems, but I did a video on these specifically where I derived these so you can kind of see where these come from, and it's called multiple steady states in CSTRs. So if you want to look at that, go watch that video, or it's also in the books. So I recommend kind of understanding enough about these curves that you can draw them and kind of figure out what's going to happen based on changing various parameters such as T naught, kappa, and yeah, I think mainly T naught and kappa, or UA. So I think that I'm not sure if these are in that module or not. Like if you go look at that, I'm not sure if you can play with the parameters of these in that module, but if not, you could write a program and then just play with parameters and see what happens with these curves. So for number 8, it says the gas phase reaction A to B over 2 is taking place in a PFR. Pure A enters the reactor at a pressure of 4 atm at 350 K. The heat of reaction, which can assume to be independent of temperature, is minus 27 kilojoules per mole of A. The rate constant at 350 K is 0.2 seconds minus 1, and the activation energy is 18 kilojoules per mole. The volumetric flow rate is 10 liters per second. When the conversion of A is plotted versus the reactor volume, the following plot is obtained, and it gives you a plot, which I'll draw. Determine the temperature and concentration of A in the reactor at the midpoint, V is equal to 50, or the volume is equal to 50, and at the exit of the reactor where the volume is equal to 100. So this is number 8. So this is gas phase. It's a PFR. And you have A to B over 2. PA naught is equal to 4 atmospheres at 350 K. The heat of reaction is equal to minus 27 kilojoules per mole of A. K is equal to 0.2 over seconds at 350 K. E is equal to 18 kilojoules per mole, and V naught is equal to 10 liters per second. And then the plot it gives you looks like this. So let's just say this is 0.51. So this is X versus volume. So this is 50 and 100. And then it looks something like this. And it says, what is the temperature and concentration at V equal 50? So T and Ca at V equals 50 and V at 100. So first of all, we already know what the conversion is at these because we can get it off this plot. So at 100, and this is drawn kind of poorly, but like if you look at the actual plot in the problems, then it's pretty apparent that at V equals 100, X is 0.95, and at $50, X is 0.25. So then we can write down the equation for concentration and for temperature. So the temperature will be an energy. So we have that. So I'll write down the concentration equation first. So this would just be the stoichiometry. So Ca, and this is gas phase, so Ca is equal to Ca naught over 1 minus x over 1 plus epsilon x multiplied by T naught over T. And we can calculate, so we need Ca naught. So Ca naught is equal to P naught over R T naught, and it gave us the information for that. And you just look up which gas constant you need. So this is equal to 4 over 0.082 multiplied by 350, and this is equal to 0.1394 moles per liter. And then we need T. So we need T because it asks for it, but also in order to calculate this, we need T. So we get that from the energy balance. Basically, any time that you're looking for a temperature or a temperature change or whatever, you always need to do an energy balance. And so for that, I am using the energy balance for, I'm assuming this reactor is adiabatic and the delta C sub P is 0. So I'm going to use this one. So T is equal to T naught plus the heat of reaction X over theta I CPI. And this will just be, theta I is 1, or theta A, so this is theta A CPA. Theta A is 1, and CPA is 30. So then we know T naught, we know the heat of reaction, and we know what X is for each temperature, so we need to calculate the temperature of each of these. So then if we plug this in and we plug in X for each respective conversion, then we get that T at 50 is 575 K, and T at 100 is 1205 K. So then we can calculate Ca for each of these. So we just go back to this equation. We put in Ca naught. We put in, so for this first one, it would be X is 0.25 and T is 575. And if we do that, we get the Ca at 50 is equal to 0.073 moles per liter. And then for the second one, we plug in the same Ca naught, and this time we put in 0.95 for X and 1205 K for T, and we get the Ca at 100 is equal to 0.00386 moles per liter. So number 9 says the following second order liquid phase reaction is taking place in a CSTR, and then it gives you a reaction. A and B are fed to the reactor at rates of 4 moles per minute and 2 moles per minute respectively. At a temperature of 300 K, the total volumetric flow rate is 10 liters per minute. Specific heats, and then it gives you those. The reactor is jacketed by water at a temperature of 40 degrees C. The overall heat transfer coefficient has been estimated at 200, and then it gives you the heat transfer area. Mixing is ensured through an agitator which contributes a work of 20 kilowatts to the reactor. So you have work in this case. If you remember, a lot of times you assume work is 0, but in this case you have work. So the heats of formation of A, B, C, and D are, and then it gives you those. So you can use those to get your heat of reaction. And let's see, the rate constant at 300 K is 0.1, and the activation energy is 30,000 joules per mole. And it wants you to find the steady state temperature in the reactor when the conversion is 90% of the limiting reactant, and then find the volume of the reactor to achieve that conversion. So I'm just going to start writing some stuff down. This is number 9. So second order, liquid. It's a CSTR. And this is your reaction, A plus B to C plus D. FA naught is equal to 4 moles per minute. FB naught is equal to 2 moles per minute. T naught is equal to 300 K. B naught is equal to 10 liters per minute. CPA is equal to 125. CPB is equal to 100. CPC is equal to 130. And CPD is equal to 135. And these are joules per mole K. And then it gives you TA is equal to 40 degrees C, which is 313 K. U is equal to 200 joules per meter squared seconds K. A is equal to 0.5 meters squared. The work is equal to minus 20 kilowatts joules per second. The reason why it's negative is because the work is done on the system. K is equal to 0.1 at 300 K. And this is liters per mole minute. E is equal to 30,000 joules per mole. And then you can calculate the heat of reaction from the heats of formation. So that was minus 60, minus 50, plus 45, plus 30. And that's equal to 35 kilojoules per mole. And this is at 298 K. And then we want to find the steady state, temperature when X of the limiting reactant is equal to 0.9 of limiting reactant. And then we also want to find the volume. So the very first thing we want to do is figure out what the limiting reactant is. So in this case, it's B. And so to make our life easy, well, we can either work in terms of B, which is a pain because all of the equations assume we're working in A, so you would have to rewrite your equations, or you can just swap A and B. So we're just going to swap A and B, and so then we're going to say that FA naught is actually 2 moles per minute, and FB naught is actually 4 moles per minute. And then we also need to swap these. So this is now, CPA is now 100, and CPB is now 125. So then this is X A. Whereas before it would have been XB. So it's still the same thing. It just makes life easier, I think, to work in terms of A instead of in B. So anyway, then we can do a mole balance. And it's a CSTR, so V is equal to FA naught X over minus RA. We need to write the rate law, and that is minus RA. So it says it's second order, so I'm just assuming that since it's second order, that follows an elementary rate law. So RA is equal to K CA CB. And then we know that K is equal to K1 multiplied by the exponent of E over R 1 over T1 minus 1 over T. And then for the stoichiometry, we have CA, and this is liquid, so CA is equal to CA naught 1 minus X, and CB is equal to CA naught theta B minus X. And then we need to do an energy balance, so I'm going to erase some stuff and then do that. The energy balance this is where you need to be careful to pick the right one, because if you were to just pull an energy balance off table 8-1, it wouldn't be right because those are assuming work is 0, but in this case work is not 0. So what you actually need to do is start with the energy balance that accounts for work, and so that is Q minus the work minus FA naught theta I CPI T minus TI naught minus the heat of reaction at this reference temperature plus delta C sub P T minus TR FA naught X is equal to 0. And then if we assume that the flow rate through the jacket is fast, so basically TA1 is approximately equal to TA2, and that's the entering temperature of the jacket and the exiting temperature of the jacket. If we assume that those are approximately equal, then we can say that Q is equal to UA TA minus T. And then delta C sub P is equal to CPD plus CPC minus CPB minus CPA. And that's equal to 40 joules per mole K. And this is another thing, like the equations, at least the first one, on table 8-1 assumes that delta C sub P is 0. So before picking which energy balance you use, first of all you need to know, okay, is your work 0? And second, you need to know if this is 0. And if either of them aren't 0, if work is not 0, you should start with this one. If this isn't 0, then you need to use the equation that accounts for this. If they're both 0, then you can probably pick an equation off that table. But just be really careful to make sure you're using one that you can actually use. So anyway, then this is theta A CPA plus theta B CPB, and theta A is 1 and theta B is 4 over 2, which is equal to 2. Because remember, we swapped A and B, so then this is what theta B is. And this is where, if you hadn't swapped those, you are working in terms of B. I mean, it's not that this is any harder, it's just that this is what we're used to working in, so it makes things easier. So then we can go ahead and solve this equation for T, because that's what we want. So if we do that, we get that T is equal to FA naught X multiplied by the heat of reaction plus delta C sub P multiplied by TR plus FA naught theta A CPA plus theta B CPB T naught plus U A TA minus work, and this is all over FA naught theta A CPA plus theta B CPB plus U A plus FA naught X delta C sub P. So then you should have everything you need to plug in and solve for T. So I'm going to erase some stuff and then, so I'm going to go through and plug everything into this equation with the units just to kind of show how everything works out, because it seemed like there might have been some questions about units. So T is equal to 2 moles per minute. So this is FA naught is 2 moles per minute multiplied by X, which is 0.9, and that's unitless. And then the heat of reaction, and it's negative, and that's basically it's multiplied by -1. So this is 35,000 joules per mole plus 40 joules per mole K, that's delta C sub P, multiplied by the reference temperature, which was 298 K. So then for this section of this equation, first of all, the moles cancel. K cancels here. So we end up with joules per minute. So, and then plus, and so then FA naught is 2 moles per minute. And this is multiplied by theta A is 1, so CPA was 100 joules per mole K plus 2, theta B was 2. And that's multiplied by 125 joules per mole K, and this is all multiplied by 300 K. So then the moles cancel, K cancels, so then you have joules per minute for this one. So that's good, because if you're adding these together, they have to have the same units. So that's one way you can kind of check what you're doing, because if you come up with, like, say, this one came up with joules per minute, and then this one you ended up with joules per minute K or something like that, then you know that something was wrong in your math when you solved for T, because the units didn't work out. So then you'd have to go back and check that. So then this is plus UA, so plus, and then this is, I'm going to move that, so then this is plus, U was 200 joules per meter second K, and then this was, A was 0.5 meters squared, and then TA was 313 K. And so then if you cancel out the meters squared and the K, you end up with joules per second, but we want joules per minute, so we need to do a conversion. So this is 60 seconds per 1 minute. So then the seconds cancel, and then you have joules per minute for this one. And then we have minus the work. So this was minus 20,000 joules per second. But once again, we want joules per minute, so we need to multiply this by 60 seconds by 1 minute. So then we have joules per minute for this one. So those should all work out to add together. And then this is all divided by FA naught, which was 2 moles per minute, multiplied by this theta A is 1, CPA is 100 joules per mole K, plus 2, because theta B is 2, multiplied by 125 joules per mole K. So then the moles cancel, and we have joules per minute K. And that's what we want because we're solving for temperature, so if we divide a joules per minute by a joules per minute K, the joules per minute cancel and we end up with K. So that's what we want for that. So then this is plus, and then see, we had UA, so 200 joules per meter squared second K, and A was 0.5 meters squared. So then cancel out the meters squared, and this is in seconds and we want it in minutes, so 60 seconds per 1 minute. Seconds cancel. And then this is plus FA naught, so 2 moles per minute, multiplied by 0.9, which is unitless, multiplied by delta C sub P, which was 40 joules per mole K. So then the moles cancel, and we have joules per minute K, which is what we want. So then if you go through all this math, you end up with T is equal to 498 K. But what we actually are calculating for this, though, is the volume. So I'm going to erase some stuff and then go through that. All right, so we just calculated that T was equal to 498 K. And so now we can calculate K. Actually, I'm just going to write down the mole balance real quick so we had calculated this earlier. So V is equal to CA naught V naught X, and this is FA naught, over K CA naught squared 1 minus X theta B minus X. And then, so we should know everything to solve for this except for K, because we know what K is at whatever temperature was given, but we don't know what K is at 498 K. So K is equal to 0.1, because this is what it gave us, multiplied by the exponent of 30,000 over 8.314. Well, it's multiplied by 1 over 300 minus 1 over 498. And this is equal to 11.9 liters per mole minute. So then we can go back to this equation, and first of all, this is going to cancel. So then we can just plug everything in. We know what V naught is. We know X because it was given. We know K because we just calculated it. CA naught was given. We know theta B. So we should know everything. So V is equal to 34 liters. So for number 10, it says the elementary reversible liquid phase reaction A to B is carried out in a CSTR. The reactor is jacketed. Pure A enters the reactor at a temperature of 27 degrees C. The following parameters are given, and then it gives you some parameters. And then it says, using the mole balance equation only, a relationship between conversion in the reactor and the reactor temperature can be obtained. This relationship is shown in the following figure as a plot of the X mole balance versus reactor temperature. And it says, show the equation that was used to create this plot for A. B, develop an energy balance equation for the CSTR, show how many steady states are possible, and determine the conversions and temperatures at the stable steady states. And C, identify at least 2 strategies for obtaining higher conversion in this unit. So I'm just going to start writing down some of the information. So this is number 10. So first of all, it's elementary. And then this is our reaction. It's reversible A to B. It's a CSTR. It's jacketed. And pure A enters at 27 degrees C, so T naught is equal to 27 degrees C. That's 300 K. And then your rate constant is equal to 1.25 minute minus 1 at 100 degrees C. And this is 373 K. E is equal to 40,000 cal per mole. Your equilibrium constant is equal to 75 at 393 K. UA is equal to 4,000 cal per minute K. TA is equal to 310 K. CPA is equal to CPB is equal to 45 cal per mole K. So delta C sub P is 0. The heat of reaction is equal to minus 75 kilocal per mole of A. V is equal to 100 liters. V naught is equal to 10 liters per minute. And FA naught is equal to 10 moles per minute. So it says plot X mole balance versus T. And it gives us what the plot looks like. So I'm just going to draw this real quick. So let's just say this is 280 here. This is temperature. This is 480. And then this is X MB. This is 1. So then this ends up looking something like this. And so it wants to know the equation that was used for this plot and then how many steady states you have. So if you remember, I want to just go through the mole balance, rate law, stoichiometry, and energy balance. So if you remember, for a CSTR, you can calculate your conversion from the mole balance and from the energy balance. So what we want to end up doing is, we already have the plot for the mole balance, and so we want to plot the energy balance. So basically X EB. And then if you remember, everywhere the XEB crosses this line, or everywhere that they meet, then that's a potential or a possible steady state. So first of all, I'm going to go through the how to derive the X mole balance. So I'm just going to erase some stuff. And also, I did a video on how to solve these problems in CSTRs, because depending on the information you're given, there's different strategies that you can use to solve. And this is one of the strategies. So I recommend watching that video on the CSTRs, and I think it's just called heat effects in CSTRs. So the first thing we want to do is a mole balance. So first of all, since this is CSTR, V is equal to FA naught over minus RA. And also, if you look in the book, actually I'm going to tell you where it's at. It kind of summarizes how to solve these CSTRs. So yeah, it's table 8-4, and it's on page 526. And it shows you how to specify the sizing of a CSTR based on what information you have. And so I recommend looking at that, and then also the video I just mentioned is I basically went over this. So it's a good thing to look at just for an ordered way to step through these problems, or through the CSTR problems, based on what information you have and also what you want, like what you're looking for. So anyway, the rate law is minus RA is equal to K CA minus CB over KE. Because remember, it was reversible. We had A to B. And so then K is equal to K naught multiplied by the exponent of E over R 1 over T naught minus 1 over T. And KE is equal to, I'm just going to call this KE naught multiplied by the exponent of the heat of reaction over R multiplied by 1 over T naught minus 1 over T. And calling this T naught might actually be a bad thing. This isn't the temperature that you're entering the reactor. This is the temperature that you know, whatever you know these K's at. So this is the temperature that you know K naught at, and this is the temperature that you know KE at. So just remember that. So then for the stoichiometry, and I'm assuming this is liquid, so Ca is equal to Ca naught 1 minus X, and Cb is equal to Ca naught X. So then we need to do an energy balance. So energy balance. And I used the equation off of table 8-1, and I used the one for CSTR with heat exchange, because delta C sub P was 0 and work is 0, so we can use that one. But we do have heat exchange because it's jacketed, so this isn't adiabatic. So X energy balance is equal to UA over FA naught T minus TA. Actually, I'm going to write this down here. XEB is equal to UA over FA naught T minus TA plus the sum of theta I CPI T minus T naught, and this is over the heat of reaction. And then this is just equal to CPA, because theta A is 1. So this is the equation that you want to plot to get this line XEB, to figure out where your multiple steady states are. But before doing that, I want to go through the rest of the mole balance and show you how the equation was obtained for this XMB. I'm just going to erase some stuff real quick. So what we want to do is combine the mole balance, the rate law, and the stoichiometry. So if we do that, we get that V is equal to FA naught X over K CA naught 1 minus X minus CA naught X over KE. And then this is CA naught B naught, so I can cancel that out. So then I'm left with V, and I'm going to actually divide over this V naught, so I have V over V naught, and I'm going to multiply the K over 2. K is equal to X over 1 minus X minus X over KE. And so then I can solve this for X, and if I do that, I get that X, and I'm going to call this X mole balance to specify that this conversion was determined from the mole balance, and this conversion was determined from the energy balance. So this is equal to K tau, because V over V naught is tau, KE over K tau KE plus 1 plus KE. And then I want to divide everything by KE, so I get the mole balance is equal to tau K over 1 plus tau K 1 plus 1 over KE. And so then we can plot this mole balance, although it's already given in the problem, so you don't need to plot it. But just taking this a step further, another way to look at CSTRs is to look at this G of T and R of T. So once you have this, G of T is equal to the heat of reaction multiplied by X mole balance. And you don't need this for this problem. I just wanted to point that out, that basically the G of T is just this X mole balance multiplied by the heat of reaction. But this is the equation that we want for this one. But if asked for G of T, then you would do this. So then we can plot this equation on to here. And if you do that, you get that you end up with something that looks kind of like this. So this ends up, these lines end up crossing in 3 different places. So you have 3 potential steady states. So to find where these steady states are, you just look at where the temperature is and where X is. So for this first one, I'm just going to erase this real quick. So for the first one, for T, you get that T right here, T is approximately 310. And you can't see that on this plot I drew here, but like if you plotted this on the computer or a lot more carefully, then you can definitely figure out where this crosses. So, but this is just to show you how it's done. So at T equal 310, X is approximately 0. And at T, this next one, T is equal to 350. So that's this one. And for that, X is approximately 0.22. And for this last one, T is approximately 412K. And for that, X is approximately 0.6. So then the few strategies you could use to increase the conversion. First of all, you could increase TA. Like, let me just write this equation again. So X EB is equal to UA T minus TA, that's over FA naught, plus CPA T minus T naught over the heat of reaction. So ways that you can increase this, you can increase T of A, you could increase U. So probably the best way to figure out what you could do to increase the conversion is to do this plot on your computer or go look at that module online. I'm not sure where it is, but I was told it was there. And just play around with values and see what increases conversion. So like for instance, if this line was shifted, then so you ended up here, then that's a higher conversion. Or if you were able to shift it up somehow, that's a higher conversion. So just play around with that and figure out what you need to do, like various things you can do to increase the conversion for that.